Hello, everyone. My name is Anand Swaminathan. I work on a team called as Flight at Lyft. Flight is a cloud-native machine learning and batch processing system. As a part of Flight, we were exposed to Kubernetes and operators. Flink Kubernetes Operator was built as a collaboration between Flight and the streaming platform. So for today's agenda, we're going to look at the Flink operator, how it has helped us run applications on Kubernetes. But before just looking into the solution, I want to show you how streaming is very critical to Lyft's business and some of the problems that we faced with our legacy deployment on the non-Kubernetes world. Then I will also show you how Kubernetes has solved these problems. We will end the talk with a demo and also leave some time for questions. So Lyft's business involves providing transportation as a service. Everything is real time. You open the app, you can request bikes, scooters, cars. You can also look at transit information in real time. So what this makes is that this makes streaming one of the most critical components for our business. If you look at this picture, you can actually see so many components that have streaming involved. For example, it goes from pricing to ETA to notifications to coupons to messaging and so on. I just want to give you a to explain a particular use case that most of you will be familiar. So if you open the Lyft app, you can see the nearby cars. And the way we do it is every car, once the driver opens the app and joins Lyft, we start sending events from the app towards the system. And this is where the ingestion into a streaming platform begins. And from there, we help you show the real-time location of the driver, the closest estimate of the time the driver would take to arrive you. And once you enter the destination, you'll also see the time it takes to reach your destination. Not just that, to maintain high levels of service, we have pricing involved, real-time pricing involved. And this is directly dependent on the amount of drivers that are near you and so on. So both pricing and ETA is one of the most critical components of our business, and they are powered by the streaming platform. So as I have shown you the use cases, it makes sure that, and I want to convey that how streaming compute framework is very important. If we rewind the clock 2 years back, our streaming involved just Kinesis and AWS Kinesis client library. So the way we did it was we built applications by writing it on Python, and we used AWS KCL with multi-Python, multi-lang daemon to build the application. But the problem was KCL was not very powerful. If you wanted to do something like aggregation or batching or grouping, you had to build all these complex systems on top of KCL. And for one example is that the way we did it was we would read the data from Kinesis using AWS KCL. We would write to Redis, and then we will have a separate fleet of workers sharded by certain regions or by hashed who would read from these Redis and then process further. So as you can see, that for doing a simple group by operation, we had to build these complex systems with having multiple systems involved, and this was really affecting our reliability. So 2 years back, we introduced Flink into our ecosystem, and it has done wonders. Flink is excellent because it comes up with a rich feature support. It has amazing functional API support for writing simple analytical applications, and you can simply do like group by, map, order by very easily in just using simple functions. It has amazing SQL support, which we critically needed. As I already mentioned, almost all our applications were written on Python, so we did not want to rewrite the application. So Beam support was very important to us, so we would instead just write Beam pipelines, which would just convert into a Flink job and then run it pretty easily. So these kind of features made Flink pretty attractive, but it came with a downside. The downside is that Flink's deployment model is a bit complex. Unlike KCL, which is like stateless, you can deploy it like any other stateless service, and it'll automatically assign shards to your workers. Flink had a topology, and that makes the deployment model complex. I will talk more about it in the next few slides. So how do we run Flink at Lyft? We have teams which write Flink application directly on Java, like ETA, and these Java applications in turn convert to a Flink job and run. There are also people who write Beam pipelines in Python. These Beam pipelines gets converted to Flink job using a Flink runner, and they're being used by the pricing team at Lyft. And on top, we have a team called as Drift. Their use case is that they take SQL queries from research scientists and data engineers, who we then convert these SQL queries into a corresponding Flink job and make sure their processing is pretty simple. As you can see that all of this is powered by the streaming platform underneath. So any investment or any improvement that you provide to the streaming platform directly reflects on all the use cases. I had mentioned to you about the complexity in the deployment model of Flink. So this is the Flink architecture. Flink has a job manager and a task manager. The role of the job manager is to act as a coordinator, and the role of the task manager is to actually do the work. The way you do it is you provide the job to the job manager. The job manager does the work of coordinating the execution by converting the job graph into an execution graph. It handles coordinating checkpointing, recovery of task managers, and so on. The task managers, in turn, have these task slots which perform a unit of work. So if you want to deploy Flink application, you have to build this sort of topology of having a job manager and a task manager, and explicitly making sure that the task manager can talk to the job manager and so on. So I will show you how we deployed Flink in a non-Kubernetes world first. So Lyft's deployment was through SaltStack. SaltStack is the configuration management system that we used to deploy all of the stateless services. This could be like any service, like authentication service or a write service, which is non-Flink. Even all stateless services was deployed using SaltStack, where we would directly say the resources that we want, and those resources would end up being created in AWS. So what we did was we wrote a wrapper or a layer in between to support Flink application. So, and how it appeared is that if you write a Flink application, we would create three things. One is we will create an autoscaling group in AWS for the job manager of size 1. Then we would create an autoscaling group for your task manager for the size that you need. And then we'll also create an elastic load balancer, which helps the task manager discover the job manager. So which means that if the job manager goes down, you need a static IP for all the task manager to talk to the job manager. So as you can clearly see that for just running one job, you need an ASG for a job manager, an ASG for a task manager, and an elastic load balancer. And on top of it, the way our deployment worked was we would first ship the bits to these ASG's machines, like how we do for any other stateless service, and then we start the service. But in our case, first we deploy the binaries to the machines, and then what we would be doing is we would log on to the job manager and make sure to start the job. If we want to deploy a new code, what we end up doing is we have a bunch of scripts where we make sure that we save point the current job and start the new job from the previous save point on the new code. So all of this was pretty manual. It was highly error prone. And that sort of thing is what we wanted to fix when we built the Flink operator to move to Kubernetes. So just talking more about the problems that we face in our legacy deployment. As I had mentioned, every single Flink job requires you to spin up a Flink cluster, which is 2 autoscaling groups and an elastic load balancer. But on top of it, if you had multiple versions of the Flink job, for example, one for staging and one for production, you would now have 2 groups of, 2 autoscaling groups, each and an elastic load balancer. So naturally, you can see that we can't infinitely create autoscaling groups. There's a clear limit. And what we ended up doing is that each team ended up creating just one cluster and started running multiple jobs inside the same cluster. Now, you might think that this kind of works because the Flink can run multiple jobs, and they all run in the corresponding task managers. But the problem is that you might end up running one high priority job, which is very critical to your business, one low priority job, which is not so critical, which can have a downtime, and your low priority job might end up affecting your high priority job. There could be a memory leak in one job, which would end up killing the entire task manager, and that would end up affecting all the other jobs in the cluster. The second biggest problem that we faced was, since we're running on AWS, anytime a node goes down, it takes roughly about 10 minutes for a new node to come up for the bootstrap process to happen, and for the task manager to join the job manager, which means that anytime if there is a node failure, which happens like once a month or or more often depending on which region you are in, we actually saw more than 10 minutes for recovery. So that is not acceptable for our business. And on top of it, you can also see that when we want to scale, let's say at 5 p.m. if you want to automatically scale, and if you want to add new task manager, that also takes more than 10 minutes for us to scale, which might not be acceptable when the traffic is suddenly spiky and you want to scale. The other biggest problem was I had mentioned the manual process involved in deployment, where we had to go to the job manager, run the script to switch jobs, and so on. So this process was like error-prone. Our configuration files were all over the place. And also some other things like, we want to do an automated rollback. Like, for example, let's say I deploy a bad code, and the code is not running. I want something to happen so that my old code comes back, and the service is just not down. So all kinds of stuff like these were not supported in our legacy system. So let's go look at the solution. The solution is Flink Kubernetes Operator. But before we look at the Flink Kubernetes Operator, if you want to run Flink application on Kubernetes using the Flink Kubernetes Operator, the way to do it is by creating the Flink application custom resource. So the Flink application custom resource is the specification that you provide to run your Flink job. So the constraint that we have is each Flink application custom resource will create one Flink cluster and will only run one Flink job in it. So if you want to say run 10 Flink jobs, the way you do it is by creating 10 Flink application custom resources. And the Flink operator would, from there, go on and do all the heavy lifting for you. There is one particular field in the specification that I want to highlight. That is the image. So when you create a specification or a spec in the Flink application custom resource, the image that we expect has to be runnable. What I mean by that is we should be able to start the job manager and the task manager from the image. Since Flink Kubernetes Operator is open source, we also have a bunch of examples inside our repositories to help you build these runnable images. But that is one of the most critical components that you have to do in order to use Flink application on Kubernetes. So while creating the Flink application custom resource, you would provide a specification. And that becomes the desired state that you expect the cluster to be. And what Flink operator does is once from the resource, it will start populating the status field. The status field is actually the current state of the cluster. And I would talk more about how the status is filled in the next slides. So when it comes to the architecture of Flink Kubernetes Operator, this diagram might look very similar to a general Kubernetes diagram. There is a control plane and there is an execution plane. What Flink Operator appears is as an extension to the Kubernetes control plane. So let me take the deployment example. Let's say if you were to create a deployment in Kubernetes, the way you would do it is you would pass in the deployment object to the API server. And the deployment object is stored in etcd. And once the object gets stored in etcd, your deployment controller picks up the object and will create corresponding replica sets. The same happens in Flink world as well. So the moment you create the Flink application custom resource, the Flink operator fetches the resource from etcd using the API server, and it will create the corresponding Flink cluster. So what is a Flink cluster in the Kubernetes world? The Flink cluster in Kubernetes world consists of the following. It has a job manager deployment. It has a task manager deployment, a job manager service, which the task manager can use to talk to the job manager, and also an ingress for the Flink UI. So you want to be able to access the UI from your laptop and so on. So for you to make any request to the job manager from outside the Kubernetes cluster, we have created an ingress for you. So this group of job manager, task manager deployment, the job manager service, and the ingress together is what we call as a Flink cluster in Kubernetes. Now let us see how the Flink operator does all of this. But before that, what is the fundamental concept that is behind this operator? So I want to talk about control loop because this is the fundamental building block of any controller. This could be a deployment controller or a replica set controller. And this fundamental building block is the same for Flink operator. The way it works is the controller looks at the current state of the world. And from the spec, it creates a desired state of the world. So what it then does is it does a diff between the current state of the world and the desired state of the world and takes an action to move the current state of the world to the desired state. So like for example, let's say if you first create a custom resource or a Flink application custom resource, your expectation is a Flink cluster with a job running in it. But in the current world, there is no Flink cluster or anything of that sort. So the operator says that, hey, there is no corresponding cluster that is existing in the Kubernetes world. So it goes and creates a cluster. I want to go through all the steps involved in the operator to explain more. But this act of control loop is one of the fundamental building block of this controller. So at the core of the Flink operator is a state machine. The way the operator works, it transitions the custom resource from one state to another. So when you first create the Flink application custom resource, what happens is you are actually in the new state. Now, there is no cluster for you. So what the operator does, it first moves the custom resource to the create cluster step where the job manager, the task managers are all created. Once the resources are created, the Flink operator then goes to wait for all the pods to come up. So there's a time duration between when you create all the resource to when all the pods start coming up. And once all the pods are up, the operator realizes that, hey, now it can go and start a job in the job manager. And it does it by transitioning to the submit job state. In the submit job state, it starts a job in the job manager. And if everything goes well, the application goes to running. So the running here is the desired state that we want the custom resource to be in. There is one more part that I want to explain before we go to a demo. I'll be showing all of this in the demo as well. So let's say you have a Flink cluster that is up and running. And now you make a code change in Java, and then you build an image. You want to deploy your code now to a running cluster. So the way you do it is just by simply updating the Flink application custom resource. So once you update the resource, the operator now sees that, hey, my desired state, that is a spec, does not match with the current cluster that I have created. So what happens is it changes the application resource from running to updating. Now, once it moves to updating, what the operator does is it brings up a second cluster for the new spec that was just updated. So which means that now, in the updating state, you have two clusters running. One cluster is the one that is actually doing the work. The second cluster is just coming up. Once the second cluster is up successfully, which means that if there is a bug and the second cluster does not come up, there is no impact to your application at all. So once the second cluster is up and running, we cancel the job in the first cluster by creating the save point, and then start the job completely in the second cluster from the save point. So as you can clearly see that if something is going wrong in your code, if the second cluster is not coming up, or if, let's say, once I cancel the job and I start the job in the second cluster, if the job submission is failing, we automatically roll back to the first cluster. We do not delete the first cluster until the job is running successfully in the second cluster. So this is roughly the working of a state machine. I want to just show you a demo of everything that I explained so far. So for the demo, this is the Flink application custom resource that I would be creating. Here is the image. All of this is available in the Flink Kubernetes Operator open source repo, so you can all try it out whenever. So this image is runnable, as in like, from this image, I can start the job manager and the task manager. There are a few other fields like, job manager config, task manager config. Essentially, these are just, indicating that how many CPU that I want for the job manager, how many, memory that I want for a task manager, and so on. Once I create the spec, I would show you that I'll start the operator, and we will see what happens. So currently, there is no application, and there is no pods corresponding to the application. Let me first run the Flink Kubernetes operator. So all of this is happening in my Docker desktop on my local. I have Kubernetes running in my local. So I'm now creating the custom resource, Flink application resource that I just showed you. And let's see what's happening behind the scenes. So currently what's happening is that the operator, let me just show you slowly. So the moment I created the custom resource, the operator picked it up. It realized that the current phase is a new phase, and it ended up creating the cluster. And once the cluster was successfully created, what happened was the operator transitioned the custom resource to a cluster starting state. What this means that, as I had explained, in the cluster starting state, we are just waiting for all the pods to come up. Once all the pods are up, the operator then goes to submit the job. As you can clearly see here, that once all the pods are up for the cluster, the operator moves to a submitting job state, and it submits the job in the job manager that was just created. And from there, you can see that once the job was started, it moved to a running state. The second thing is, even though the cluster is currently running, the operator is continuously monitoring the existing cluster. So let's say if the task manager is down, or if there is any issues with the Flink cluster, the operator continuously monitors the existing cluster and updates the status field of the Flink application resource. So let me just show you what I exactly mean. So as you can clearly see that for every application that you create, we poll the corresponding Flink cluster and notify the status of the job, how many checkpoints, number of healthy task managers, and a bunch of things that we monitor from the existing cluster, and we store it in the status field of your application, which means that if you want to monitor your application, you can literally just read from the status and see what's exactly happening. And on top of it, we also emit metrics for all your failing applications. Let's say if your application suddenly started failing, we have metrics emitted for all of these, which means that you get alarms on top of metrics automatically. Now, there's one more thing that I wanted to show you, and that is what will happen if I go and update my application resource. So for that, let me just start the threads. These are just polling and the resources. The operator is still running. So now what I'm doing is I am going and updating the Docker image part of it. So my YAML, is exactly the same, just that the image is different. Meaning, let's say if you update your code, you'll build a new image, and this would what happened if you were to do a deployment of your new code. Yeah, let it go through. Let me just slowly explain what's happening. So when I went and updated the existing custom resource, the operator found out that the current custom resource does not match the existing cluster. So what it does is it brings up a new cluster in place and waits for the new cluster to come up. Once the new cluster is up, as you can clearly see that once the new cluster is up, it moves from a cluster starting state to a save pointing state, where we cancel the job from the existing cluster and try to start the job in the new cluster. And as you can clearly see that the save pointing has succeeded. We have started the job in the new cluster. And once the job is started in the new cluster, you can see that the existing cluster is automatically terminated. So the first cluster that was running the job is now terminated because we were able to successfully launch the job in the second cluster. So this is an end-to-end example of how Flink Kubernetes operator was able to, take all the updates from your application resource and translate that to a corresponding cluster. So what is the impact of all of this? The moment we moved from our legacy system to running Flink application on Kubernetes, as you can clearly see, we have one Flink job per Flink cluster. There is no sort of interference. All high priority jobs run separately. All low priority jobs run separately. Scaling is super fast. And anytime a pod goes down, Kubernetes does a great job of bringing up a new pod pretty soon. So we get the advantage of just migrating from a non-Kubernetes world to a Kubernetes world automatically by just transitioning, by just using the Flink Kubernetes operator. The second biggest thing that we noticed is that during a deployment, there was no downtime at all. Meaning that whenever if someone is deploying a buggy code or a code where the permissions were badly configured, this never happened. And the main reason was of the auto rollback support. Anytime we were not able to bring up the second cluster, or if we were not able to start the job in the second cluster, we would automatically roll back to the first cluster. And what we saw was there was actually no downtime in many cases, but even the downtime in some rare cases was pretty low compared to what we have been seeing in the previous legacy system. The third was the configuration became much easier. Anything that we want to deploy, we had to create a corresponding Flink application resource. So we wrote wrappers on top of our existing Flink application resource to set these default values for task manager, for the number of task slots for task manager. So any user who wants to run a Flink job just had to write like 3 to 4 lines of code, and he would have the Flink application running in Kubernetes. Lastly, we saw a huge cost saving because of all of this. As I had mentioned, in the previous world, we had one Flink cluster that was highly provisioned because we did not know how many jobs we would end up running, and we did not want to roll the cluster frequently. So we created like these we used big machines, EC2 machines to run these monstrous Flink clusters. But in the new world, each Flink cluster is just running one job. So since you know the job that you're going to run, you can provision the resources that you exactly need, and this helped us save a lot of cost. So what is the current status of the project? So all of this is open source. Any of you guys can just go to GitHub Flink Kubernetes operator, start the operator for your business or your use cases immediately. We call the project status as beta because it helps us do some backward incompatible change in case if something is needed. We have had excellent support from the open source community. We have like 5 contributions from people outside Lyft. There are teams, there are companies like Trade Desk, Lightbend who are actually using the operator and evaluating the use cases today. Lastly, if you have any questions or if you want to use Flink Kubernetes operator, please join the Slack channel. This is a public Slack channel. We have like 40 members. They might answer your questions, or you can post any of your doubts or your specific use cases, and we would be happy to help. Lastly, my team at Flight is giving more talks tomorrow. There is one tomorrow morning at 10:55 and one at 5:20 in the evening. If you are interested in running like large-scale machine learning jobs or large-scale batch processing job, I would highly recommend you guys to come check it out. Also, Flight is also open sourced. We open sourced Flight a month back, so it's also something that you can immediately adopt and start using. There's also a happy hour today evening. If you guys are interested and want to talk to other engineers at Lyft, let's meet at Thorn, Barrio, Logan. I think it's a beer spot, but yeah, why not? Thank you so much. Happy to answer questions. Ask for questions. Yes. Any questions? Feel free to. Oh, sure. Hey guys, just one thing. We have flight stickers right here. So if you guys want flight stickers, feel free to come pick it up. Thank you so much. But yeah, go ahead.
So you talk about the ingress that is generated per cluster. So how do you avoid conflict between the ingresses?
Sorry.
How do you avoid the conflict between the ingresses, between the different clusters?
So each Flink cluster will have a separate service and a separate ingress. And the way we do ingress is by the host path. So let me actually show you a demo. That's actually a great question. It was part of my demo, but I missed it. So this is a Flink application that is currently running in one of our Kubernetes cluster. And you can actually see the top part of the URL. So what we have done it is when we create an ingress, we specify the application name in the host path. So which means that each host path will now point to a corresponding ingress, which will then route the request to the corresponding job manager. So that's what we have done. And also it's configurable. So what we have done it is if you want to use an operator, Flink Kubernetes operator, you can specify your own custom ingress path for you to run it in your Kubernetes world. No, it's a part of the config map. So essentially what we do is you specify like the regex of how you want to create the ingress URL, and we would, while creating the ingress, automatically set that particular path in the ingress. Thank you. More questions?
Yeah, I have a question about save. Well, what are you saving and where are you saving it?
Sorry, what is that?
In your save point. In your save, you mentioned saving state or
yes.
What are you saving and where are you saving it?
So, that's a great question. So in Flink, what happens is you have a Flink cluster running. There's like a bunch of checkpoints. Each task manager creates their own checkpoint of the entire graph. So what happens is that when we want to change code from one cluster to other, the way we transition is by creating this save point. Save point is a concept in Flink. We store all our save points in S3, and the path of the save point is stored in the Flink custom resource. So for example, so you can actually see that, okay, we should have done it during the, yeah, right here. So if you look at the restore path, so for my example, I'm using a local store, but what we do is we store all the save points in S3, and the path of the S3 would be available here, which means that when we start the new Flink cluster, we say, hey, start the new Flink cluster from this particular save point. More questions?
Did you use KubeBuilder or one of the other frameworks?
What is that?
Did you use the KubeBuilder SDK or one of the other frameworks?
She's asking if you use KubeBuilder or if you use some other framework.
Yeah, so we started off with using Operator SDK to build the Flink Kubernetes operator, but we wanted to do some low-level things as well, so we ended up directly using controller runtime. So controller runtime is also open source, is something that we use directly for building and running Kubernetes operator. What I mean is, yep, this is what I mean. So we use this particular package, Kubernetes controller runtime, to build Flink Kubernetes operator. We used the operator SDK before we moved to this, but since we wanted support like multi-namespace, we want the operator to read only from specific namespaces. So for building like these sort of like complex use cases, we had to use controller runtime directly.
Thank you. Hi. Since using this operator, it seems like each job will have its own cluster. So do you have like a plan to provide a centralized user interface for all the jobs when they are running in independent Flink clusters?
Oh, that's a very good question. As a part of this project, it's not, but that is something that we have been talking for a while. Since that now you have all the jobs running separately, you want a UI which would show the aggregate of all the jobs. Not directly, but one thing that we are trying to do solve that is using integrations with Flight. So think of it this way. Apart from Flink, we also run Spark. And Spark also does similarly. So you want to just have an overview of not just Flink jobs, but Spark jobs or any other batch processing jobs that's running in the cluster. So as a part of this work, it's not, but we are trying to solve some of that using our integration with Flight and other part of it. So yeah.
Thank you.
Yes and no, yeah.
I have another question.
Yes.
So if one job will use one Flink cluster, it might be expensive. So what is the overhead for running the admin kind of servers for Flink?
That's a very good question. So if you actually think of it, the overhead is actually low, which is what I mentioned from the cost saving that we had noticed. So if you were to run, let's say if you were to run 2 jobs in a single Flink cluster, you now have to see that both the jobs, the memory of both the jobs has to be taken into consideration, which means that if, let's say, one job is high memory, low CPU, and the other guy is like high CPU, low memory, you will have to like do some sort of math to make sure that both of them are running reliably. But if you were to just split it up into separate jobs, you can just tune the exact amount of resources that you'd end up creating. The only overhead on top of that is that we're running multiple job managers. So for example, instead of having one job manager, we are running 2 job managers per Flink cluster. So it's like times 2. But if you actually see that the amount of CPU and memory for a job manager is actually not that high. So we run it with like 6 CPUs and like 50 GB memory. So if you actually do the math at our scale for the reliability benefit that we get, it's like hundreds of thousands of dollars a year, which is not that much.
I think we're pretty much out of time.
I think there's one more question.
Do you want to just come up? Because I think,
Yeah, so when you were talking about your like legacy infrastructure, you had like your autoscaling capabilities took a long time. When you switched over to this Kubernetes-based deployment model, did you allow for like horizontal node scaling, or did you say, okay, now if you're starting to, get to the limit of your cluster's capacity, you add a node, or like how did you guys deal with that? And then if it was automated, like how did that reduce your node scaling time with that?
That's a very good question. So currently, there is no trigger-based autoscaling in Flink. So what I mean by that is, let's say that you have a Flink cluster that's currently running, and suddenly, let's say at 5 p.m. the traffic is higher, and you see that there's like a curve of increase in CPU and memory. We don't automatically have like triggers to say that, hey, when the CPU is more than 70%, automatically add new task managers. The way we do it at Lyft is that by updating the parallelism of the custom resource. So if you actually look at the spec, right, we have a field called as parallelism. So that is the spot that needs to be updated. So today what we have been doing is we have a script wherein we update the parallelism. So essentially what parallelism does is, based on the parallelism and the number of task slot per task manager, decides the number of task managers. So by just updating the parallelism, we go through this path of adding more pods. The difference is that in the previous rule, you had to add machines. Now we just have to add new pods, which was the huge improvement. But to answer your question, trigger-based autoscaling is what we are planning to build in the operator itself, so that you can have certain triggers which would make the Flink cluster scale automatically. But I believe Flink is also doing work in this regard to automatically scale horizontally. But it's also in the roadmap of Flink Kubernetes Operator.
Yeah, and I have one more question. It's
Sure.
back to the cost discussion. So in terms of like the ratio of cost savings that you have, did you go from 100 to like 50% of your overall initial cost, or what kind of proportional?
So that's a very good question. So the cost, let me state this. So we have like more than 100 applications that we're running in the non-Kubernetes world. We have migrated roughly like 30%, mainly the ones that are low reliable. For example, Drift runs 40 Flink jobs in a single Flink cluster, and it will go down always, like every 2 weeks. So when we migrated 40%, we saw roughly a 20 to 30% reduction in cost. But again, this number depends on how well you tune the job manager and the task manager config. In our case, what happened was it just came to like 5 different teams, and they did a good job of setting the right values. But if you end up setting like extremely high job manager or task manager resources, you might not end up seeing the cost benefit. But it comes down to how you accurately you set the resource for your job.
Yeah, and that goes back to kind of the higher level view of across your jobs and like what's your utilization, right? Like actually measuring your utilization to manage the cost.
Oh yeah, that's true. Actually, one more thing on the cost side. Since you mentioned, we have another way of doing cost. The way we do it is we have a service called as Infraspinatus. I think there is another KubeCon talk on it as well. That guy would take metrics from all the pods and drill down by namespace and give us a view for the cost. It doesn't address the fact that it can't tell you how many Flink jobs are running in the cluster, but it will definitely tell you the cost per namespace. So that's one way for us to look at the cost. Awesome. Thank you, guys.